Hi, everyone. Thanks so much for joining today. My name is Brandon Rodriguez, and I work at NASA's Jet Propulsion Laboratory in the Education Department here in Pasadena, California. Very excited to have you guys join us today. This is your first time. I'll kind of give a run through about what you can expect if you've been here before. Thank you so much for coming back. I'm really excited about today's topic. We've spent so long now talking about Mars throughout the summer as we prepared for the launch of Perseverance. And you'll notice last month we kind of made our first step talking about the Deep Space Network and this kind of transition to how it is that we manage all of our missions, not just going to Mars, but how do we communicate across the solar system. With today's talk, we're actually going to expand even beyond that. And that's what I'm really excited about. I'll tell you that this topic is of personal interest to me, as this Saturday we have a follow-up session just for educators. So if you're a teacher, there are a few slots left for our workshop this weekend, looking at student and teacher programs in astronomy. So we'll actually have several of my student interns presenting on their research in astronomy and looking at young stellar objects. So to that end, this is a really a double interest, not just as a general topic, but for my own personal research to be able to understand better how it is that we use the entire electromagnetic spectrum to study space. So beyond just visible light, how are we using wavelengths such as in the infrared to study well outside of our solar system to stars and nebulas and galaxies far away. So we have a great guest. I'm going to turn it over in just a second to Jose. But before I do, I'll tell you a little bit about the format for today. We'll have an awesome presentation from him. We'll do a little Q&A. If you register online on our website at the JPL Education site, you'll be able to submit questions to us, which we'll answer here with Jose. And if not, feel free to just continue to listen in. And after that, after that Q&A section, we'll do a little recap of other resources from the education department for you, either as a student, a teacher, a parent, or maybe just someone who's generally interested in what NASA is up to. So with that, let me not delay and turn it over to Jose, who's going to tell us about infrared astronomy and a really exciting new mission.
Thank you so much, everyone, for joining us today. Thank you, Brandon, for the introduction. My name is Jose Siles, and I'm the manager and technical lead of a new NASA astrophysics balloon mission called ASTHROS here at NASA Jet Propulsion Laboratory. We're planning to launch from Antarctica this mission ASTHROS in 2023, but that's a few years ahead of us right now. I wouldn't call this a clash, actually, but rather an exploration journey or even an adventure, because it's what science is all about, right? In this case, this is an amazing journey, or pretends to be an amazing journey, to fly a giant far-infrared telescope from the most remote place on Earth into the stratosphere to study the stars. And in fact, what you see here in the first slide, if you're seeing it right now, this is a photo that I took of our team on Antarctica back in 2006. So when we were there, it was actually 24 hours of light every day. It was daylight all the time. But a few months before we got to Antarctica, an NSF photographer took this amazing photo from the US McMurdo station. I hope that you can see it. It's beautiful. I mean, every time I see it, I'm impressed about it. I wish I could have seen this in person when I got there. Unfortunately, when we got there, it was already daylight. But anyway, I'm sure that everyone will recognize what it is, right? Of course, this is our galaxy, it's the Milky Way that you can see there. But have you ever taken a second to really understand this view? Because the Milky Way spans 100,000 light years across, which means that if we are on one side of the galaxy, we'll have to wait 100 years to receive emissions from a star that is on the other side of the galaxy. So when we look at the sky, we actually are looking into the past. That's what we see. So somewhat, when we design our radio telescope, we are designing a time machine because we're looking into the stars. Another important thing here is that just in our galaxy, there are between 200 and 400 billion stars. Can you imagine at all how many galaxies are in the universe? Because I certainly cannot. But if we could, and we multiply the number of how many stars are, for example, in our galaxy, the the total number will literally blow our minds. So you will believe me then if I tell you that with so many stars in the universe, it's obvious that they have to play a key role in the evolution of galaxies, like our galaxy that you see here now. So basically, if the stars play a major role in the evolution of galaxies, they also play a major role in the evolution of the universe. However, believe it or not, galactic evolution is still one of the biggest mysteries in astrophysics, and we still need to do more missions to understand what's going on. I like always to say that galaxies are actually living entities. So we have these gas and dust. So all these galaxies are filled with this gas and dust, what we call molecular clouds. And due to gravitational effects, they collapse to form stars. And when that process happens, there are molecular emissions in the far infrared that tell us what is going on in these processes. For example, you can see in here, we have ionized carbon, ionized nitrogen, and atomic oxygen that are being emitted as the star forms. And then eventually planets form, and after millions of years, the star dies, for example, at these huge explosions that we call supernovas. And then all that material is ejected back to the interstellar medium, and the cycle happens over and over and over. So at every step of the cycle, actually, there are emissions in the far infrared that tell us what's going on in this process of star formation. So and remember that every atom of our bodies was producing one of these cycles in one of these stars. So don't forget then that any scientific mission starts with a question. And coming back again to the idea of that every atom in our body was forming a star, the question we're trying to solve or to find answers to is indeed where we're coming from and if there could be life elsewhere in the universe. So this is again the universe as we see today with our bare eyes. It's an optical image that any one of us could take just integrating with a normal camera for a long time. Again, the Milky Way in the center. And now you guys will think, well, that's a pretty quiet and relaxing image of the universe, right? It doesn't seem that a lot is going on after you just told us about the gas collapsing and the star formings and supernovas and so on. And yeah, that's right. You're right. This is a very quiet image. But if we go to the universe in the far infrared, what we cannot basically see with our eyes, this is infrared wavelengths, so our eyes cannot capture them. Now you see all the gas and dust surrounding the stars, right? So it's not quiet anymore. So in all these gas that you see in this image now, they're star-forming regions. They're star-forming. So to understand all what's going on here, we need to build this far-infrared radio telescope able to capture these gas, but not only in the three-dimensional space, but also in dynamics. So we need a 3D map of how this gas moves so we can really understand the processes. Because to explain a little bit better how it is, every molecule of the gas, so we're mentioning carbon, ionized carbon, and nitrogen, and so on, it emits at a certain frequency. So we can tune our receiver at each of these frequencies, and we assign a color is when we get maps at wavelengths that we cannot see with our eyes, like the one that you see here in the infrared. Let's zoom actually into bottom right corner of that image. And that's a nebula there that I'm sure that every one of you guys can recognize in the sky, called Orion. And this is a spectral image taken with the Herschel Space Observatory in the far infrared. And all these emissions or all these lines that you see there are life-enabling molecules, which means that at a certain point, it could be part of a life form. In fact, 50% of the luminosity emitted since the Big Bang is emitted in this frequency range in the far infrared that, as I said, we can see with our bare eye. So that's why it's so important to study the universe in these frequency ranges. So once again, we want to understand where we're coming from, and that's why we want to receive all these emissions. But the far infrared has a problem, and the problem is that we cannot see these emissions or all these emissions are mostly blocked by the atmosphere. Not only in the far infrared, but also in the ultraviolet and the X-rays. But if we just focus right now in the far infrared, the water vapor in the atmosphere block this signal, and that means that we cannot put a ground telescope to observe them. We have to go to the space or very close to the space, like, for example, a balloon. Let's think about this as if you have a cell phone, able to receive signals from the stars. And let's try to go to the Atacama Desert in Chile, for example, at 4 kilometers altitude, where ALMA is. I'm sure that everybody had heard about ALMA. And let's see if we have coverage. So the answer is no. Well, you can still receive some signal from a star formation in very far away galaxies because they move very fast with respect to us, and the frequency change enough. So now the frequency is much lower, and we can still see them with ALMA. But if we're really focusing on galaxies that are nearby, or star forming regions in our galaxy, we definitely cannot see them from the ground. Okay, so we can say, let's take an airplane. Let's put the sample of the NASA SOFIA observatory. Okay, you can see here that things get better. Your now stellar cell phone gets much better in terms of coverage. But there are still a lot of dead zones in critical points or critical emissions where we want to see what's going on. All right, let's go a little bit higher. And now we have a balloon flying at 130,000 feet into the stratosphere, pretty much 4 times the altitude of a commercial airplane. And now we are over 99% of the atmosphere, above the atmosphere, and our coverage, of course, become pretty good. You can see that now our stellar cell phone has close to 100% coverage, and we can see all the signals where the coverage was 0. Now the transmissivity is much better. So that's one of the reasons, and one of the most important reasons for doing far infrared missions with balloons. But it's not the only one. Another important one is, of course, cost. So we have ground telescopes like ALMA. We have said already that for this specific case, we cannot use it, but we could. We're talking about $1,000 million. We can go to an airplane, as I said before, like SOFIA, and we're talking about close to 100 million per year in operations. Now, of course, we can go to space. It's another $1,000 million. A space mission will give you better conditions and a lot of observing time. But because of the cost, the technology has to be very mature, has to be very well proven. And then it takes a lot of years to make it happen, since you have the idea until you fly. But with a balloon, we can do science missions with around $10 million. And because of the lower cost, we can take higher risks and accelerate the infusion of the new technologies to test them in flight and pave the way to future space mission. But in addition to that, we can train the new generations of scientists and engineers that at some point will become leaders on space missions. So it's a great training camp for these new generations. And also, of course, we can land the radio telescope back on Earth after the flight and update it and fly it again. And the technology that we use in balloons is not only, for example, we're talking here about astrophysics, but the same technology, talking, for example, of this mission that we flew in 2016, called STO2, or the technology that we're going to fly on ASTHROS in 2023. So the same technology can be used for detecting, for example, water in ocean walls like Europa, the moon and Jupiter, or in comets, or to monitor our planet's health, for example, the ozone layer, or even to look at humidity and rain forming inside the clouds to improve weather predictions, basically to improve our life on Earth. All right, so we're talking about balloons, and I'm sure that now maybe of you are thinking, wow, using balloon is a great idea that you guys just had. But some of you probably instead are thinking, what are you talking about? Balloon is a rudimentary flight technology and has been around for many years. And you're correct. Balloons have been around for many years. In fact, NASA's first balloon mission was in the 60s, and it was called ECHO. It was a passive reflector for communications, inflated in space at 1,500 kilometers. So it was used for communication, but did some measurements as well of the atmosphere. But do you really think it was the first scientific balloon mission ever flown? Think about it for a minute. And the answer is no. So actually, in 1912, Victor Hess took a hot air balloon and went all the way up to 5 kilometers, measuring the radiation as a function of altitude. And in 1936, he received the Nobel Prize for discovering the cosmic rays with an experiment from a scientific balloon. So more than 100 years ago, which to me is really impressive. And since then, more than 1,000 missions and still counting. So yeah, indeed, balloons are not something new. So we have been doing it for more than 100 years. All right, so I'm sure that at this point, and after all what I've been talking about balloons and astronomy, you already know that radio telescope is not more than a radio. But instead of tuning to your favorite music station, we just tune to our favorite star emission, to these ionized carbon or ionized nitrogen or atomic oxygen emissions. But there's a problem or a caveat here, and it's the frequency. So a regular radio, for those that remembers the old radios working at around 100 megahertz, uh, a radio telescope like the one that we are building is working at 20,000 times a larger frequency, which means the circuits, the receivers that we need to capture these signals are much, much smaller. In fact, the receivers we need to fabricate to detect the emissions from the stars fit inside a human hair. So that adds a lot of complexity, of course, to building this radio telescope. Okay, so then we take these circuits, we assemble into housing blocks, and then we put them into a cryostat filled with helium because we need superconductors to be able to detect these signals. They are very faint signals, so we need a very low noise and very good sensitivity. So we need to operate at 4 Kelvin, close to the absolute zero. So then we attach this cryostat to a big antenna. It was 0.8 meters for STO2. It will be larger in ASTHROS. We threw in there some motors and reaction wheels to control the pointing, because of course now we are hanging on a balloon, surfing the airs in the stratosphere. So we're basically getting a ride, and we need to constantly point the radio telescope to our target. We need car batteries and solar panels for power the telescope, and of course antennas to receive the data and for communications. And then after all that is put together, we have our telescope that you can see in the slides here. Altogether, around 20,000 parts. I haven't counted them for sure, but it's an estimation. From very, very small parts to large parts that you put together in 4 years and test it here first in the US to make sure it works. And when everything is working, surprise, we need to take it apart, put it in boxes, ship it to Antarctica, and do it again. And do it again in 3 weeks. So it's like, are you kidding me? You have gone to this point where everything is working and you're going to take it apart? So yeah, that's what we're doing. Exactly what we're doing. And why Antarctica? Well, the first thing is safety. If something goes wrong, there's no risk for people or infrastructures. The worst thing that can happen is maybe a big hole on the ice. You have to basically do a crash land, but not a big deal, right? But the important thing is that we want to take advantage of what we call the Antarctic vortex, because we have this circular wind pattern that forms in the summer in Antarctica, and that pattern makes the balloon, when we launch, circling around the continent for a few weeks, and then since it doesn't goes outside the continent, we can land and fly again next time. So that's another advantage of doing it in Antarctica. So Antarctica, here we go. The team gathers in LA after taking everything apart and put it in boxes, as I've said before. We leave from LA a few hours in Sydney to transfer to New Zealand and give us some time to visit the Opera House, of course, which is beautiful. Then to Christchurch, New Zealand, for survival training and getting the cold weather clothes and all the orientation and prepare to go to Antarctica. And from there, we take a US Air Force plane to McMurdo. So pretty much this is the process. We start with my luggage that you see here, and you will be thinking like, why is so interesting to see your luggage? Well, my luggage, in fact, is not interesting, but there's some black boxes that you see there, which are actually parts of the telescope, because these parts, some of them are so sensitive, so delicate, that we need to carry them with us. We cannot just put it in a ship for 6 months. We need to make sure that they are transported correctly. So it's really funny to go to the bottom of the wall with a box full of things that you can imagine how it looks in an X-ray in the airport. So it's it's an interesting process. Then you get there, you can see there a photo of me with all the cold weather clothes. It's not that I wanted just to put the photo there for social media. It's just that they make you wear these clothes when you get into the airplane. And the reason is that if something happens, I mean, if there's an emergency and you have to land in the middle of the nowhere in Antarctica, I guess that maybe you can survive a few hours. You have a warm clothes. Probably not much more than that. And then, yes, we get into the airplane and we fly as cargo. But look how much leg room you have. It's much, much better than a commercial flight. So we get to Antarctica, and the runway is just ice. It's a very nice runway, which is just the frozen sea, pretty much. So it's a very interesting experience. You have McMurdo Station here that looks like, of course, all scientific base. You can see the main galley in blue somewhere there. You can see the dorms and maintenance buildings and so on, everything you need to survive for the 800 people that are here in the summer. During the winter, when it's nighttime all the time, we're talking about just 40 or 50 people. We have a galley, we have a clinic, a small clinic, a fire station. We have a beach, a frozen beach. And you have something very interesting, which is this hat there that Sir Robert Falcon Scott built in 1912 when he was doing his exploration to the South Pole. So it really feels when you see this kind of thing like you are one of these explorers from the early 20th century. By the way, 1912 was the same year that Victor Hess did his balloon experiments, which is a nice coincidence. And a lot of ice. It's Antarctica, so you have a lot of beautiful ice, like you can see here. We were not building the telescope in McMurdo. We were in a NASA facility called Long Duration Balloon Facility. That's where we have to rebuild the telescope in 3 weeks. And you can see here a nice day. And when you have a storm, basically everything gets wiped out in minutes. So you go from having an amazing view to not seeing anything. And that's why you really need a survival training, because if that happens, you better just put your tent there and don't move, because you have crevasses on the ice and all that. So you don't want to be wandering around without really seeing where you're putting your feet in. So that's why it's important as well, all this training. Inside the hangar, it's quite comfortable. We have heaters, of course. But it's obviously not easy to bring things to Antarctica. It's not obviously easy to rebuild a telescope that you have built in 4 years in 3 weeks. And you need to make sure that you brought everything with you that you need and everything you might need to fix anything that might go wrong. Because if not, it's like Apollo 13, the movie, if you guys remember, when they have to build these CO2 filter adapters with whatever they had in the spacecraft. So Antarctica is the same. If you miss something, you have to do it yourself. So believe me, it happens. So where are the stars in Antarctica? Right? We're building this telescope, but now we have to look at the stars to try it. But it's 24 hours daylight. And I have told you before that the atmosphere blocks all these infrared signals. Okay, so we don't have the stars, or we cannot receive from the ground the emissions from the star. Well, let's create our own star. Easy, right? So we put a transmitter simulating a star that you can see in front of the telescope. We send the signal to a reflector antenna, and we point the telescope to this reflector antenna that now is a fake star. It's an artificial star, but allow us to basically make sure that the telescope is pointing to the correct position and that we receive the signal of the stars. And there's another advantage of creating your own star, is that if you want to make sure that you are pointing to the right star, well, it's easy. You go there and switch off the star. So what you do in this case, you go there and you put your hand with an absorber in front of it, and if the signal disappears from the telescope, great, you were pointed to the right place, and then you're ready to fly. So as I said, 4 years, 20,000 pieces back together with all the cables and receivers and solar panels and the telescope and the parachute and the software, cables, everything working in 4 weeks to get to the point where we are ready to launch. In this case, that's from STO2, beginning of December 2016. And so our time machine is ready here on the right. The flight configuration on the left, you see the 400 feet balloon, 400 feet diameter, is as large as a football stadium with 40 million cubic feet of helium. It doesn't look fully inflated because of the different pressure between the ground and the stratosphere. It launches like that, but when it arrives to float altitude, it's just a perfect sphere, and it is at that point fully inflated. So it's connected to the payload that you see there, very tiny, hanging from the launch track. It's connected with a 900 feet cable. So let's see now a video how we got to this point and how we launch. So, well, I cannot see the video myself in the image, but what is going to happen basically, you start with inside the hangar. You're going to mount the payload into the telescope, and then the payload and the telescope is connected to the gondola. When that happens, all the solar panels are connected basically around the telescope. You can see all that process. Once you have everything mounted, you're going to basically try to wait until all the electronics work, and you're going to go outside and do all the communication tests, make sure that you can monitor the telescope, and you can basically make sure that you can command it, that you receive the data and everything. When that's ready, you go back inside, you wait until you have a launch opportunity. And when you have a launch opportunity, you have to go outside, do all these tests again, and basically when the air is calm, you wait to go to the launch pad and you release the balloon. So the balloon gets released. So basically you see it is not fully inflated, as you saw in the picture and you'll see in the video. You release the balloon climbs slowly. It basically gets aligned on top of the launch vehicle. And when that happens, you backtrack the launch vehicle, you release the balloon, and then basically the radio telescope start climbing, and you have to basically back off in order to avoid the radio telescope to hit the hanging structure where the telescope is hanging from. Then it start climbing to the stratosphere. It's a 2 hours climb. At the beginning, you'll see that it's spinning a little bit. It's not a big deal. When you get to float altitude, you have reaction wheels basically to point at that point the telescope and avoid the spinning. You also have an elevation drive to do the pointing, so you're sure you're pointed at any specific target at any given time. You'll see also in the video the view from inside. So it's very impressive when it gets released, how close you get from the launching vehicle. As you climb, you can see also the Mount Erebus, which is a supervolcano that is there in Antarctica. So it climbs. We fly for 21 days. And after 21 days, what happened is, for terminating the mission, we tear the balloon apart. And for that, we just release a mechanism. You'll see the balloon basically breaking apart. And very, very small on the bottom, you see the parachute deploy, the payload and the parachute deploying to basically land back on ice. There's an image. You can see how tiny the payload is compared to the radio telescope compared to the huge 400-foot balloon. And you can also see the view from the altitude, how the Earth looks like from that altitude. And at the end, you land back on ice, and you basically can recover and eventually fly again. So I don't know if the video is still playing. Maybe Brandon, you can give me a sign when it's over.
That's good.
Okay, so if you have ever seen the guys at JPL missions control during a Mars landing, so see how fancy it is. But for balloons, it's as exciting. You have seen the video and all this process of the launch and operation, so you can imagine how exciting it is. But it's not quite fancy in Antarctica. It's like your garage. It's very cool because you're in Antarctica, definitely very cold, but not as fancy as JPL, indeed. We're working inside the hangar. We haven't slept for many hours at that point, but pretty much if you compare the two photos are very similar one to each other. Less people in Antarctica than in here at JPL for a Mars landing, but as I said, the same excitement. We flew for 21 days. Here is the path. And we look for a sample into one of the most active star-forming regions in our galaxy, the Carina Nebula, that you can see here. And in the right, this is raw data. This is the data as we receive it with the radio telescope. In the lower right, you can start seeing peaks, and those peaks are actually carbon emissions. Those peaks give you the velocity of the gas and also the abundance, and you can turn that into an image. And that image that you see in red in the center of the screen shows actually that there are stars forming in that region in the Carina Nebula. And this is actually when we can say that it's mission accomplished. It was a long journey to here, but the mission was a success. But the only way to make it happen is teamwork. This is true for any scientific mission. Teamwork is the key, but even more for a balloon when you spend 24 hours a day for 3-4 months there on the ice, 4 years before, but especially when you go to Antarctica, it's 24 hours working together, living with these folks, and you really need to trust each other and get along to make it work. And that really makes these scientific balloon missions from Antarctica so special. Just sharing these moments with the team there is just extremely rewarding. And then, of course, as I said, we can fly again. The answer is definitely yes. Let's take a rest first. And you will see here some penguins at the end of the season taking their rest. The team did the same. And now, a few years later, we did take our rest. And a few months ago, we started working in a new mission that is going to fly in 2023. And I already mentioned the name, which is ASTHROS. And what you see here is a different different graphics, but it's the same star forming cycle that I explained before. And what we are going to focus on ASTROS is how supernovas, this huge explosion, modify the gas and then regulate the star formation. Because otherwise, all the gas will have collapsed into a star really fast in the early universe. But we know that that doesn't happen, that there are a lot of star formation going on. And that's what we really want to study with ASTROS. But what we're going to do is to fly a telescope which is 3 times larger in diameter, 9 times larger in collective area, because we want to see outside of our galaxy and inside of our galaxy and compare those galaxies or those star-forming regions in different states of evolution. We're going to fly newest technologies that we have now. For example, we are not going to use helium liquid in this case. We're going to use an electrical cryocooler, so that means that we can fly much longer. And also we can reduce weight, and that allow us to increase the size of the telescope, which in this case, as I said, is 9 times larger in area. But again, that's 2023. We're very excited. We'll be in Antarctica in a few years to launch these new exciting missions. But I'm going to finish, while we will until 2023, with this paragraph that I wrote in 2016 after the STO2 flight, and says the following. Today, we got the first detection of carbon emitted by nearby Eta Carina 7,500 years ago. That's the time the signal takes to get to Earth from the Carina constellation. Carbon is basic to life, and these carbon emissions we are seeing today might turn into life in several million years from now. So likewise, ourselves, our carbon was probably part of a distant star-forming region millions of years ago. So today, as we look at the stars from the most remote part of our planet, using a large telescope on a giant balloon, we dig into our past to try to understand our future. Thank you very much, and happy to take any questions now.
Really, really awesome. Thank you so much for that. I learned a ton. This is a really interesting kind of look at this new technology that's old technology, right? But doesn't get hyped the same way that a lot of these missions do, right? I mean, like you said, we kind of hear about the big missions to Mars and so forth, and the big crowded rooms, and we see how many hundreds of people work on this. But this, those are expensive and time consuming, and to hear about these kind of recyclable and kind of quick turnover types of missions, that's pretty amazing. We got a ton of questions that I'm hoping to ask you. I'll start with a few technical ones while it's fresh in our heads. You kind of mentioned close to the end that you're switching away from the liquid helium, and that's going to allow you to be able to kind of stay afloat longer. Is that the limiting factor, or did you get the information you needed, or like how long would you want to stay up if you could, to have a complete mission?
Well, the ASTROS mission, when we fly, our baseline science is 21 days. But that's mostly defined because, the Antarctic vortex sets for 3-4 weeks, right? So when the winds are gone, you run the risk of drifting off continent and losing the payload, right? Because we'll have to recover in the water, and that's not possible. So you want to finish the mission before that happens. But for a future space mission, you could fly longer. You could try to basically fly a superpressure balloon and recover, for example, in Chile and other places, or maybe the wind pattern lasts for more weeks. When you have helium on board, you are limited by the amount of helium that you have on board. So basically, it could be like 2 weeks, 3 weeks, something like that. So once you run out of helium, your superconducting receivers don't work. So it doesn't matter if you can keep flying. The balloon will keep flying, of course, as much as you want until you terminate it. There is no, in principle, no limitation on that other than you wanted to recover on the ice. But if you run out of helium, you just cannot keep doing science. However, if you have electrical cryocooler, there's no limit to that. So you could keep flying as long as your winds are settled and you can still take advantage of them. But also we said in the beginning that we want to do this to infuse the technology in future space missions. So for example, there was a mission, a similar kind of technology called Herschel that I talk about a little bit. And Herschel lasted 3 years on space because it had 3 years of helium. So now we flew a new mission similar to that one, but with a cryocooler, then we won't be limited to 3 years. So we prove it in a balloon in a similar kind of mission, then you can then, or you are ready to put it into a space mission. And
Interesting.
That's one of the goals.
That was kind of my follow-up question, which is, what is the advantage of this? Why not fly a ton of balloons instead of a Herschel and a Spitzer? So you're saying that the technology you're testing now will feed into that. Are there any other technical advantages of why we would want to, be in space instead of just orbiting with a balloon?
Well, of course, the atmosphere is perfect in space, right? In balloons, you're over 99%, but you still have some impact of the atmosphere. Also in space, you're collecting data, for years constantly, pretty much. In a balloon, you fly for, let's say, 4 weeks, and then you have to land back, and then you have to wait another year until you can launch again. So you basically are taking science in periods of 1 month at a time. So it's much cheaper, but you have to do it more often. So it depends on your science. It might be just easier and enough to do it with balloons. Maybe you have to take data for so long and you have already your technology ready, and you want to go to space. Or it's somehow in between, right? That you can do part of it still in the on a balloon. You take the opportunity to fly very fast new technologies that otherwise will take like maybe 10 years to get to the point where you are ready to go to space, qualify somehow to go to space, and then once you have demonstrated in a balloon, just go to the next step and prepare your flight mission. But you know that at that point you have accelerated the maturation of the technology.
Yeah, very cool. Another question was actually about that turnaround. So now that you've been up and you've got your data and you have this parachute where you're hopefully landing safely, so you can turn around the payload. What is the velocity when this thing hits the ground? What's the risk, and what does repair and testing and recycle look like?
It's a very mild landing. I don't remember exactly the number, but it's just a very few meters per second. Like it's a very smooth landing if everything goes well. You have some some pads that somehow helps to make the landing a little bit softer. Actually, you have seen in one of the slides how the payload looks like right after recovery. Of course, the solar panels are damaged after landing, but those are very cheap and you don't care about that. But the rest of the structure and the telescope is all working. Actually, we switched everything on in the ground after recovery and everything was working, which was pretty impressive. We could basically fly again in the same configuration. Now, of course, you always want more, right? And that's why the balloons are great. You want, at that point, 4 years later, you have newest technology, and that's what we want to do in ASTHROS. Now we, based on the same kind of science case or trying to go a little bit beyond, but also similar technology, but now we want to have more receivers. So it's like a camera. You want more pixels. You always want more pixels to be able to get better images. You want a larger antenna because you want to go now to extragalactic sources. With the flight that we did in STO2, the telescope was so small, so we couldn't really look outside of our galaxy. So you want to expand it, make it larger with things that you have already proven and fly again. So the new gondola is actually probably 3 times larger than that one because the telescope is 3 times larger in diameter. So if that looks big, the new one is going to be much more impressive.
Yeah, there's never good news, right? Because it's always, now we have more questions. Now
exactly. I would say that no matter what you give to the astronomers, that they always want more, and that's how it's supposed to be, because that means progress, right? We try to aim for very difficult or impossible things, right, and make it happen. Like they're mighty things, right, as we say at JP.
From the balloon side, has there been any evolution in that technology? What is the balloon made out of? Is there progress there, or is that kind of understood?
The balloons, the NASA balloon program office keep evolving the balloons. For example, this balloon we used was a zero pressure balloon. You can fly as I said, a few weeks. They are working now in a super pressure balloon that can fly much longer and go through day-night cycles. The material of the balloon is no different to the material that you will have in a supermarket bag, in a typical supermarket bag. It's a 2 millimeter thick plastic polyethylene, and so yeah, it's not very special if you think about it. It's as well very well understood material and process.
Yeah, the chemist in me appreciates like that pressure is doing the work, right? As you mentioned, it doesn't even look full at where we are when the pressure is kind of collapsing the balloon, but as it reaches altitude, that change in pressure allows it to open up.
Yeah, we go in the ground we have one atmosphere, and we went to 130,000 feet. The pressure drops between 0.3 millibar and 3 millibar, and that what makes basically the balloon to span and fully inflate. But you of course have to calculate very precisely the amount of helium you put in the ground to have the correct inflation at altitude.
Yeah, so for kids at home wondering why Boyle's law and Charles' law, why these are important, this is
exactly all the mass and get it right, because you cannot go up there and try to inflate it on the fly, right? So
one more technical question for you. Why infrared in the first place? Why are we looking there and not like Herschel, was looking at other wavelengths. So what is it about infrared that's so interesting?
Well, Herschel had many instruments. One was hi-fi that was exactly the same, similar frequencies, the far infrared of some millimeter waves, as we call it as well. I've gone through that in the presentation very briefly. So part of the reason is that 50% of the luminosity since the Big Bang and 98% of the photons basically were emitted in this frequency range. And that's something that Covey, a previous NASA mission, discovered. So talking now about the star formation, pretty much all the key tracers that allow us to understand every single step of the star formation process are in the far infrared. It just happened to be there, which is not surprising because of what I just said, that many of the missions since the Big Bang are in this frequency range. So that's why, for example, just to mention a specific case, ionized carbon and ionized carbon and atomic oxygen are the major coolants of the star forming regions, which means that when you have all this material collapsing and the temperature increasing, there has to be something that cools down the molecular cloud so the star keeps forming. So basically that collapse doesn't get interrupted. So that happens because of emissions of ionized carbon and atomic oxygen, which are in this far infrared. So if you are able to detect those signals, you can infer that this star forming process going on there.
Awesome. If we could talk a little bit about you and your journey to JPL, several people are wanting to know. I mean, how did you kind of get into this path? I mean, I'm sure you didn't take some high school science classes saying, "Oh, I'm going to Antarctica to send balloons," right? It's pretty niche. So how did you get to where you are now?
So that's an interesting question, actually, because I mentioned Apollo 13 during the presentation. Apollo 13 is very important for me because I watched I didn't watch the launch, of course. I mean, I was not born back then, but I watched the movie when I was 15 years old. And I remember that scene where they were trying to fix that problem and bring back the astronauts alive, back to Earth. And I was just, I fell in love with NASA. I was from a small town in Spain, in Andalusia, a very small town. I was a little kid. I saw these NASA engineers working together and doing impossible things, and I said, wow, that would be a dream to work in a place like that. But when you are not American, and I couldn't even speak English back then, it's not that my English now is very good either, but it's much better than it used to be back then. So I got impressed, but I thought it was impossible, right? How you get to here. So I just wanted to play with technology. So I studied electrical engineering after high school. And then I got just by chance into a project for the European Space Agency through the university to design or to do modeling for this kind of receivers. And at some point I started through conferences meeting people also from JPL, and I ended up doing my PhD between Madrid, Spain, and in Paris, in the Observatory of Paris, working on this kind of technology. And eventually, I got a Fulbright scholarship to come here at JPL as a postdoc. And again, that was like a dream come true, right? And you get here and say, I hope that at least I can be here for a few months. Let's see if I'm good enough. And but as you know, when you get into JPL, everything is so exciting and so many projects, and it's been 10 years since that first day. And it's an amazing place to work, and for me, it's like fulfilling a dream. I just love what I do, and and if even you get to go to Antarctica and fly things from there, it's just impressive. It's something that I couldn't have thought about when I was 15 years old, and I thought it was an impossible dream to work for NASA.
Yeah, it's such a it comes up so many times when we do sessions like this for our international audience is always wondering how can I make this happen, and it really does seem like those not just agency but university partnerships kind of create some inroads. So it's really kind of motivating to hear that.
Yeah, and I think that's the key point. I think you never should say to yourself that something is impossible. I think you just need to do the best, just to enjoy it and enjoy studying and enjoy your research, and eventually things happen. And that's the key part of it. I was a normal guy, like every one of us, every one of the kids that probably are watching us. I just need to do what you like to do, and eventually you get where you want to be. And of course, there's hard work, and sometimes you have to be in the right place in the right moment. But it is not impossible. It's more doable than what we think when we're little kids.
Yeah, most definitely. And as someone, I've only been here now for 5 years. This is not my first job out of school, and that's totally fine. I wish our students understood that you don't always hit the home run. You don't always get the dream job on the first stop. I was fortunate enough to have a great job coming up, but obviously when NASA called, it was that time. So you work hard and you kind of chip away at it sometimes, but you do get to these awesome places and do research as incredible as this.
And there's another important point, which is not being afraid of making mistakes. It's difficult to send something to Mars, but it's also super difficult to send something from Antarctica to the stratosphere in that tight schedule. And you can basically put that sample to any project at JPL or at NASA. You just need to trust yourself, trust the people you work with, and not be afraid of making mistakes, because you never get it right at the first time. So you just keep going and keep trying, and you learn from your mistakes, and you get to the point where we can land amazing rovers on Mars, for example. So that's something that is very important, as well as you go through your student life, to realize that you shouldn't be afraid to get it wrong the first time, or the other way around. I think that you learn more from the mistakes than if everything was perfect. So that's another key point for the students, I think.
Yeah, it's such a great message to kind of wrap up on that. In this day and age where students are so afraid of getting the wrong answer and thinking about grades and kind of the next step, college, grad school, etc., that the real world really does appreciate failure and iterative learning and kind of growth in that way that maybe we don't see in the way that school is kind of typically run.
Mm-hmm.
Well, thank you so much for joining us. I really, really appreciate it. It's just awesome to kind of get this insight as to crazy cool missions to look forward to in IR astronomy. If there's a seat in that cargo plane next time, please take me along. But yeah, thank you so much for your time today. We really appreciate it, and I'm sure everyone really enjoyed. Thanks so much.
Yeah, thank you for having me. And definitely, let's hope that everything goes well. And 2023, maybe we can do another one, but this time from Antarctica, and we can talk to everyone and show things real time as they are happening there, doing this an event like this from Antarctica. So thank you again, and thank you for everyone that is listening or watching us. Hope everyone enjoyed, and yeah, thank you so much for the opportunity.
Great. So with that being said, I'm going to transition to a few slides again on some educational resources and just further reading exploration that you guys can do if you're interested in this topic and you want to learn more. On my first slide here, you'll see just kind of our landing page. This is the JPL education website. And you'll see up at the top, there's a banner of options here, ranging from intern to share, where you guys can kind of walk through different types of activities and resources based on your interests, whether you're a teacher, whether you're independent learner, or you just want to read a little bit more about what's happening at JPL and NASA overall. On my second slide, you'll see some of these lessons that we have in that teach section. Again, if you're an educator, whether in the classroom or at home, we're really trying to explore this further. Why is color and wavelength important for understanding our solar system? And in fact, you'll see a stack of images on the top taken at different frequencies, really giving us very, very different information. And so we heard a little bit about why infrared is interesting, but again, beyond that, different wavelengths really tell us different things about what we're looking at. And you can model this in the classroom or at home using different things like filters, which we'll hear a lot more about on this coming Saturday, as we kind of model actually some of these activities and look at how light and filters interact with different objects. On the third slide, you'll see another example lesson. This is kind of our take on the old cereal box type of spectrometer. And this is really interesting when you look out into space, where again, maybe the visible light, like you see in the left-hand picture labeled A, gives you something, but clearly something's different in B, where you start to get a little bit more of the where chemistry and physics come together, much to my delight. And you can see a little bit more about kind of the atomic subtext. What elements are there? Like we heard Jose mention about looking at things like carbon and oxygen. We know that every atom kind of has a very specific spectrum. So matching that light against known spectrometers and filters, we can actually see what elements are being contained in some of these images. On slide 4, you heard us mention last week, if you attended. If you didn't, this is recorded and on the website, talking about not just how color, like and by virtue of wavelength, is important, but again, how distance is important too. How does light move across space? How does it expand and dim? And how is it that we're able to communicate with spacecraft as we send them further and further into the solar system and beyond? So we have a lot of demos and activities around that as well. So on slide 5, you can, again, this is kind of our news section written for the general audience. You can read more about all of these topics. There's drop-down menus to kind of walk you through different categories of things, whether your interest is more on internships, education, or just, again, kind of current events from JPL. On slide 6, you'll see a closer look at our teach section built for educators, which, again, really easy to navigate website, has these drop-down menus so that you can target what grade you're interested in. You can search for individual topics and themes so that you can really get to where you're going. And this, again, is something that we'll highlight in our Saturday session just for educators. The same thing on slide 7, where, again, this is written a little bit more for self-directed learning. So if you're a student or you want to assign a lesson to your class or to your children at home, this is written with the idea that they would run this themselves. They're able to kind of follow step by step and do these little online labs and activities to learn more themselves. On slide 8, you'll see our education resources overall from a web page called Learning Space. And here you'll kind of get a feel for a conglomerate of all of these things put together for students. So all of these activities, we have video tutorials that we filmed, translated into Spanish, and just kind of frequently asked questions for families as well, as we kind of navigate this wild world of distance learning and the schools potentially being closed where you are. And then lastly, I'll tell you guys that if you want to learn more, we have put together a kind of thematic exploration just on this topic on our Teaching Space website, where you'll be able to find all of our activities, images, games, etc., all aligned to this kind of light and astronomy theme. And you'll see that at the Teaching Space website, where you can kind of navigate and learn more. Really, really beautiful images. I highly recommend taking a look. So with that being said, I'll wrap up. I thank you guys so much for joining us. I hope that you're really enjoying these events, this monthly series. I'll remind you guys that these take place monthly. They're recorded and placed on our Teaching Space website. So please tell your friends if they can't make it, they can always rewatch later. And they're always followed a few days later on the weekend for an educator-specific session where we'll just have teachers and really explore some of these lessons and the offering of activities in a hands-on kind of conversational way. So I hope to see you next month. We're going to look at ocean exploration and a little bit of oceanography. So if that's of interest to you, I hope you'll dial in. And thank you guys so much for joining us today. Have a great day.